Okay, so let me begin by saying a couple things. One is about this thing about asking questions. I absolutely want people to interrupt me at any point if what I said was unclear. And on Zoom that I'm used to, you can see everybody else, and I can see if people raise their hands. But at this point, all I see is my own slides in front of me, which means I guess you just have to yell at me, okay? So if you want to ask a question, you just have to not be shy and turn on your mic and just start talking until I'm aware you're there. I'm sorry about that, but that at the moment seems to be the only solution. I guess the other thing I want to say to begin is that I waited a little late to prepare these slides, and I had planned in my mind to do a lot more than it now seems to be reasonable to do, given how many slides it took for me to lay out just the first thing, the first measurement problem in my paper. I'd actually hoped to go over all three of those and another one on top of that. But it just doesn't seem to me reasonable to do, especially for people who haven't really gone through this before. And also because the standard way that the measurement problem is discussed in much of physics is wrong. I had planned to talk about this. I'll mention this now. I don't know if I'm going to get to it. It's certainly not in the slides. But let me just give you a very quick example of what I mean. It's very easy to find people who say things like, decoherence solves the measurement problem, right? They will use those words. And I'm not at this point going to try to go into decoherence, what it is. All I need to say is that for the first problem that I lay out here, it's absolutely clear that decoherence doesn't solve it, can't solve it, doesn't have a chance to solve it, which means that many physicists don't understand what the problem was to start with. They don't understand what Schrödinger was worried about when he came up with his cat problem that I'll talk about. And if you don't understand the problem to start with, then of course you don't appreciate what a solution to the problem is. So if I can just get across this main problem in a completely clear way that everybody understands, I'll be happy, and also everybody will be 2 steps ahead of most people, sad as that is. Okay, so let me just start through this. And so I'm just going to really try and work through in enough detail and slowly enough the thing in my paper I call the problem of outcomes, which both can sometimes be called the measurement problem, other times can be called the problem of Schrödinger's cat. Those names are actually kind of different. It's not clear the cat situation that Schrödinger sets up really corresponds to a measurement. It's not clear that measurements play any particular role in what this problem is. So I think the problem of outcomes is a bit better, because certainly the issue is how to understand that certain experiments have certain sorts of outcomes, or what kind of situation would you be in if you were forced to deny that? All right. So the way I have this set up is as a set of 3 propositions that are jointly incompatible, right? You logically cannot hold all 3, or epsilon close to logically cannot hold all 3. And that's nice and clean, because it forces you to ask yourself the question, which one of these am I going to try to give up? So I will be going through first just the 3 propositions, and then the argument, then we'll talk in more detail exactly about how all this stuff goes. So the first proposition is this thing I call 1A, that the wave function of a system is complete. The term complete goes back to the paper of Einstein, Podolsky, and Rosen in 1935. As far as I know, that was where it was introduced into the literature. And it's clear what it means to say that a representation of something is complete. It means that the representation manages to represent all of the features of the thing you're representing, right? Many representations, maybe most, are not complete. If I take a picture of you, that's a representation of you, but it's certainly not complete because it doesn't show the back of you, for example. I can look at that picture forever and not know what is on the back of your shirt. So it's a kind of incomplete, a partial representation. And what one hopes to get out of a completed physics is certainly a complete theory that manages to capture all of the physical features of a system. And in quantum mechanics, we use a mathematical gadget called a wave function. We ascribe that to systems. And so you would think that somehow or other, this wave function represents some of the physical characteristics of a system. And the question that Einstein asked, Einstein, Podolsky, and Rosen asked is it a complete description? Does it represent everything physical about the system? The measurement problem, or the problem of outcomes that I'm going to set up, takes as one postulate that the wave function is complete. The paper of Einstein, Podolsky, and Rosen was arguing that it can't be complete, that you get into absurd results and you get spooky action at a distance and weird stuff if you think it is complete. But most physicists, certainly Bohr and Heisenberg and the founders of the Copenhagen interpretation or Copenhagen spirit or whatever you want to call it, insisted that the wave function is complete. That was very central to what they were arguing. And there were various things that were thought to be proofs. I don't know if we'll have time to go into that. So that's our first proposition, that the wave function is a complete representation, somehow or other, of all the properties of the system. The second proposition is about the evolution, and as you will see by the 6 in the middle of Schrödinger, I have not actually proofread these. I have not proofread these, so they're probably going to be full of typos like that. The wave function is a function of time, and so it evolves. There's going to be an equation that expresses how it evolves in time. And the second proposition is that equation is a linear equation, which I'll go into much more detail exactly what that means. That has a very precise mathematical meaning. And that is always what the evolution is governed by, a linear equation of motion. So that's a clear mathematical proposition. And the third proposition is that measurements, or we could just say experiments, again, it doesn't really matter if you call an experiment a measurement, that experiments like the things we call spin experiments always have determinate outcomes. That is, at the end of the experiment, the device is either in a state which indicates, say, spin up and not spin down, or spin down and not spin up. Now, again, if you replace measurement here with experiment, everything goes through just the same. If you don't see the difference between a measurement and an experiment, maybe a simple example will get that across. Here's an experiment you can do right now. Take a quarter, flip it, let it fall to the ground, and look at what you got. Okay, that's clearly an experiment. And we would normally say that, except in extremely strange cases, it has one of two outcomes. It's either heads or tails. And it's not in any obvious sense the measurement of anything. You would not say there's some feature of the quarter that got measured by flipping it once and seeing whether it came head or tails. But you'd certainly say, okay, yeah, I gave you an experimental protocol. You could carry it out. And whenever you carry it out, you get one of two outcomes, heads or tails. Good. So we're going to, the third proposition is that various experiments of the kind we'll talk about have always outcomes of the sort that we think they have. So
question.
Yeah.
Sorry for the interruption.
No, that's
can we just
exactly what I want. That's fine.
go back to last slide? Would you mind, I guess, come up with some sort of definition or clarification in terms of the measuring device and why there's a need to mention the measuring device?
The only reason, again, you could rewrite 1C the way I just said it and take the word measurement out and just say experiment. Okay, that is what we're going to do is we're going to run into problems trying to reconcile quantum theory with the world as we take it to be. And the world as we take it to be has lots of stuff in it. Some of it is experiments and measurements. A lot of it just cats walking around and stuff like that, that in no obvious sense is a measurement or even an experiment. But there are just lots of what we take to be plain facts about the world. Like if I toss a coin and let it land on the ground, it'll come heads or tails. Right? Take that as an example. Again, it's not really a measurement. It's, because I told you what to do, it's a kind of experiment. The important thing is that we think, except in absolutely extraordinary circumstances, it always has one of two possible outcomes. Right? And if someone were to come along and tell you, no, that's not true, right? It's not the case that when you flip coins, they land either heads or tails. You'd be, in the first place, extremely puzzled what they were telling you. And in the second place, if you somehow managed to accept it, you'd be extremely puzzled how to reconcile your experience with that. Because your experience of the world sure seems to indicate that when you flip coins, they come either heads or tails. So I hope if I, by rephrasing it that way, I can avoid having to talk about measurements, because what a measurement is doesn't really play any role in this problem. That's why, in a way, calling it the measurement problem can be slightly misleading. Okay? Well, I'm going to take that as being okay. So now I have some slides. Again, I think I'm just going to be repeating things I just said. What do I mean by saying the wave function is complete? Just that every physical feature of an individual system, we ascribe wave functions to individual systems. Every physical feature of that system is somehow represented or reflected in the wave function. Go back to the coin case. It's we think a plain physical fact about a coin on the floor, that it's either lying heads up or heads down. And therefore, if I had a complete physical description of that coin, that physical description should somehow or other indicate which way it's lying. If it didn't, you would think, oh, well, you have not given me a complete description of the coin, because here's a fact you haven't told me about. It follows from the fact that the postulate that the wave function is complete, that if I ascribe the same wave function to two different physical systems, then they are physically identical in all respects, because otherwise, if there was some physical difference between them, it wouldn't be reflected in their wave functions, which by hypothesis are the same. So that's all that completeness means. And let me go in just to make absolutely clear. And again, this is not because it's a complicated concept, but because it's so simple, and you just want to be absolutely secure that you understand what's being said. Let's take the example of classical electromagnetic theory. The way one normally learns that theory, initially anyway, is that Maxwell postulates two, at the time, novel physical entities, an electric field and a magnetic field. which had not been part of physics before that. And Maxwell says, look, you know, we need to understand these phenomena. We have to believe in these new objects, these E and B, as we call, I mean, I'll call them the electric field and the magnetic field. Then when I have boldface E field and boldface B field, that's a way to indicate their mathematical representation. They're represented by vectors, a vector field, a mathematical vector field, which is why the E and B are bolded here. Now, according to Maxwell's theory, that's it. If you tell me what the electric and magnetic field are in a certain situation, you've told me all there is about electromagnetism, the electromagnetic situation. In order to do that, I can give you mathematically an E field and a B field as mathematical vector fields. But as I assume everybody is familiar, I can do something else that turns out to be convenient mathematically. And instead of using the E field and the B field, I can use a vector potential A and a scalar potential phi. And in classical electromagnetic theory, A and phi are, in a certain sense, not considered to be real the way that E and B are. And I just want to get, you know, again, we just conceptually very clear about this. The reason is because from A and phi, you can derive E and B, but different A phi pairs give you the same E and B, right? If you hand me a set A and phi, it's a mathematically easy to derive what E and B have to be, but different such potentials can give me the same electric and magnetic field. So if you think that what really exists, what's really real is the electric and magnetic field, those different A phi pairs are all both equally good representations of it. And then we say, oh, the difference between them is merely a gauge transformation, right? And the gauge transformation that takes you from one A phi pair to another A phi pair doesn't represent a physical change at all. Those are just different mathematical representations of one and the same physical situation. And in fact, in classical electromagnetic theory, that gauge freedom, the freedom to pick a gauge however you want, is why you use A and phi. Because at a practical level, you can pick gauges that make the particular mathematical equation you have to solve simple. So it might be hard to solve it in one gauge and easy to solve it in another gauge if the gauge is chosen to reflect symmetries in the problem. And so if you were a classical physicist, you really got used to doing these picking gauges and making gauge transformations as a calculational convenience. But you didn't worry about that choice of gauge as having any physical significance. Exactly because you didn't think, in a certain sense, A and phi are real. Nonetheless, and so this is the moral of this, everybody at that time would agree that A and phi are complete. That if you give me, if two systems are described by the same vector and scalar potentials, then electromagnetically they're identical. There's no difference, physical difference between them. So those are clearly complete descriptions, even if they're, as it were, not real in some sense. So I hope the notion of completeness is now clear. Good. So that's the situation with our first postulate, that the wave function somehow is a complete representation of the physical of a physical system. The second postulate has to do with linearity, and again, I just, maybe everybody knows this, but it never hurts to go over it slowly and painfully. Has a clear mathematical meaning. We have these wave functions. The set of all the wave functions that are available forms mathematically a complex vector space. which means that if I have any two wave functions, psi and phi, and any complex numbers, alpha and beta, then I can take the linear combination alpha psi plus beta phi. That's going to be another wave function. Now, you can, if you want, you can restrict this to normalized vectors. That's fine. It doesn't really matter. The point is that for any pair of wave functions, you can, as we say, superpose them, which just means taking linear combinations of them, and you get another wave function. Then a function on that vector space is linear if, when you apply that function to alpha psi plus beta phi, you always get alpha times the function applied to psi plus beta times the function applied to. That's linearity. It's a very straightforward mathematical characteristic of a function. It means it's up to you whether you want to add these two vectors together and then apply the function, or first apply the function and then add them. You get the same result either way. An obvious function that is not linear is a squaring function, because it sure makes a difference whether you add two numbers and square the result or square the numbers and add the result, right? Then you don't get the same answer. So this is a very clear, precise mathematical characteristic that a function can have. And since the dynamics of a system, which is just an equation that tells you how the system evolves through time, is a function, give it an initial state and it spits out a later state, you can ask whether that function is linear or not, assuming that it's over a vector space, right? And it either is or it isn't. And the second postulate, so as I said, you can either add the vectors and then apply the function, or apply the function, then add the outputs, you get the same result. Now, Schrödinger's, the particular evolution equation we're interested in here is the Schrödinger equation, which is certainly a central equation in quantum mechanics. And it is a linear equation. And I hope, again, everybody has seen this, but just to see where that comes from and why it's so important, the Schrödinger's equation is given at the bottom. So you have the time evolution of psi of t, and that's just equal to this operator h hat, the Hamiltonian operator applied to psi. And the point is that the h hat operator is a linear operator. The Hamiltonian operator is a linear operator. That's a fundamental assumption that's in quantum mechanics. The reason why it's important to see this is you have to understand how deeply these postulates are embedded in various approaches to quantum mechanics. You have to see that, for example, the problem we're about to talk about arises from the assumption, partially just from this assumption of linearity. In my experience, many physicists do not understand this. So, for example, I have had lots of experience of physicists who, if you talk about the problem of Schrödinger's cat, as we will, say, oh, you know, the cat has 6 times 10 to the 23rd particles in it. Nobody has ever has or ever will write down the wave function of a cat. And that's true. That's absolutely true. Nobody will ever in the history of mankind write down the specific wave function of a cat. But it's completely irrelevant, because the thing that causes the problem is the assumption that Schrödinger's equation, which will be applied to any wave function, whether we can write it down or not, is linear. And the fact that the cat is very complicated and the cat has many degrees of freedom and this and that is just completely irrelevant. The only assumption is that whatever the wave function of the cat is, it evolves linearly. And if you want to deny that, deny it. But denying that is a very different thing than noting that cats are kind of complicated things. Okay, so the Schrödinger equation is in fact a linear equation. And what does that give us? Well, what we're going to do here is now use these arrows here to represent time evolution and have a subscript for the initial and final state. So the Schrödinger equation, let's assume that the wave function is always governed by Schrödinger's equation or by any linear equation. Then we have that if the time evolution takes us from psi initial to psi final, psi I to psi f over some period of time, and the same equation takes phi initial to phi final over that same period of time, then of necessity, just from the linearity, if we were to start out in some linear superposition of psi and phi initial, that would evolve into the same linear superposition of psi and phi final. And that just follows from linearity, and you can't get out of it. And that, as I say, that follows no matter how complicated psi and phi are, no matter how many degrees of freedom they have, no matter whether we can write them down, no matter we know what they are. That's just from the linearity of the dynamics. Okay, so now we're in a position to state the problem. I'm going to change the problem in this form goes back to this paper of Schrödinger, which, if you've never read it, which would not be surprising, is a wonderful paper. And it was written in 1935, the same year that the Einstein-Podolsky-Rosen paper was written. And it is, in fact, a response to the Einstein-Podolsky-Rosen paper, although not a response in the sense of an argument against Einstein, Podolsky, and Rosen. It was at the beginning of that paper, in a footnote, Schrödinger says, this paper is more like a confession. That is, I think the Einstein-Podolsky-Rosen paper induced Schrödinger to think about the problems with understanding quantum theory in a clearer way and a more profound way than he had. And he was struggling with what to say and trying to explain why the prevalent understanding of quantum theory couldn't possibly be correct. And he was induced to do this by the EPR paper. So in that paper, Schrödinger famously imagines what he calls a diabolical device, where he couples a Geiger counter and a vial of poison, and there's a little radioactive source in such a way that if the Geiger counter clicks, the poison will be released, and if it doesn't, it won't. And he takes for granted, as we all do, that apart from ethical considerations, there would be no problem building such a device, right? We could make such a device. He imagines it with the radioactive source at such a low level of radioactivity that what we would normally say is that within an hour, there's a 50% chance that there'll be a decay. And so we put this device in the box, we put the cat in the box, we seal the thing up, and we wait an hour. Now, for reasons that will, I hope, become clear, just because it makes it cleaner, I'm going to alter the device a little bit so that the poison releasing mechanism will be triggered not by the radioactive decay, but by a flash of light that occurs on a photo screen. In particular, we're going to imagine coupling it to a device that sends an individual electron through an inhomogeneous magnetic field, which is the thing we normally call a Stern-Gerlach magnet. And when that electron hits the screen, there'll be a flash of light, and we put in a photodetector such that if it picks up a flash of light, it will then trigger the vial. right? So the standard picture, as it were, and I just pulled these off of Wikipedia, the standard picture for the Schrödinger cat experiment has this little radioactive box. That's the trigger. And then you see either the hammer comes down and breaks the vial or it doesn't, as it were. This is actually in the Wikipedia article, they're complaining because the main thing is to look on the right side of this picture where you have two possible outcomes. Remember, this is supposed to be the problem of outcomes. And the normal way to think about this that Schrödinger thought was obviously correct is that this experiment has two possible outcomes. They labeled 1 and 2 there. Either the device is not triggered and the cat ends up alive, or the device is triggered and the cat ends up dead. Now, the way I want to update it is, again, to have the trigger not be this radioactive source, but I've stuck a Stern-Gerlach experiment in the place of that. And what you see is that you have a beam. In this case, it'll just be a single electron shot the box labeled 1 and collimated, and then through this magnet with this funny inhomogeneous magnetic field, because the magnet on top, the north part, has a pointy part and the south part has an anti-pointy part, so you get an inhomogeneous field. And the effect of this, and you can just check in the lab, is that when I shoot a single electron through, it either gets deflected upward or gets deflected downward. It either appears at one of the two spots that are indicated by the 5. It either appears having been deflected, as it were, toward the north or toward the south. Now, this whole story about shooting the electron and deflecting it and so on, that's not really important here. What's important is that I push a button at 1, and a little bit later, always, either there's a flash at the upper location or a flash at the lower location. And that's just something you go in the lab and check, and you say, yeah, it just looks like, just like flipping coins always end up either heads or tails, this device either gives me a flash up or a flash down. And then I've indicated with this blue cylinder a photo detector, which is then, if it picks up the flash at the lower location, is going to trigger the device. Okay, so we could build such a thing, and it would be a physical system, and we want our physics to be able to account for what it does. Now, again, I'm not sure how much people have done a lot of quantum mechanics, a lot of spin, just to make sure everybody's on the same page. Notice the Stern-Gerlach device, that magnet, is oriented up-down, what we'll call the z direction. There's no reason why we can't twist it in space. We can twist it sideways, for example, so that the axis is horizontal. When it's upward, we'll say we're measuring, these are just words for it. We're measuring the z spin of the electron. If we twist it, we'll say we're measuring the x spin of the electron. And if we twist it, again, we only get one of two outcomes. Either the flash is, as it were, toward a position deflected toward the n, or it's toward a position deflected toward the s. And we call those spin up and spin down outcomes. Okay, so we have this device, and it's a real physical kind of thing. Now, here's a fact maybe everybody knows. We can prepare electrons in a state we call z spin up. We can prepare a beam of electrons in a state we call z spin up, so that every single electron in the beam sets off the flash in the upper part, and we can create a state that we call z spin down in a beam, where every single electron in the beam creates the flash in the lower location. That's just something we can do, and we need to account for that. Clearly, there is a physical state where the electron is guaranteed to go up, or the flash is guaranteed to be high, and another state in which the flash is guaranteed to be low, and we just call those states z up and z down. Now, we're ready to run the argument, okay? And let's just go through it piece by piece. We can create such a device, and we can set it to run so that if we feed in a Z up electron, so the flash is definitely going to be up, that will certainly evolve into a final state where the cat's alive. Right? Because the flash will be up, the photodetector will not fire, the diabolical device will not be triggered. And that time evolution we represent in this schematic way on the bottom, that starting with the device in its ready state and feeding in a Z up electron will evolve into a state in which the cat is alive. If the wave function is complete, that has to be true. Why? Because actually the cat does end up alive, right? And if the wave function is complete, then it's got to end up in a quantum state which represents the cat being alive. So this is supposed to be just something we can verify about this kind of apparatus. Whenever you start it out in the initial state given, it ends up in the final state given. And similarly, if we feed in a Z down electron, then the flash always occurs in the lower part. The photodetector always goes off. The poison vial is always broken, and the cat always ends up dead. So we must have this kind of, if the wave function is complete, and remember, that's one of our postulates, if the wave function is complete, we must have this kind of evolution that's starting with the device being ready and the input electron Z down, we end up in a state where the cat is dead. And now we need just the final fact, the last thing to get this to go, which is that, as I said, we can not only prepare electrons Z up and Z down, we can prepare them X up and X down. We can twist the device and prepare electrons so that relative to the twisted Stern-Gerlach apparatus, they're always either deflected toward the pointy magnet or away from the pointy magnet. And we have such states, we call them obviously X up and X down. And then the key fact, which is the third thing there, that mathematically, and this is just a mathematical fact, that the X up state is a superposition of the Z up and Z down states. So this is the set of spin states forms a complex vector space, which means vectors can be written as linear sums of other vectors. The Z up and Z down states form a basis. So you can write every state as some kind of linear superposition of Z up and Z down. You can write every state as a linear superposition of X up and X down. They're both bases. So I can write the X up state mathematically as a linear sum of Z up and Z down. And similarly, the X down state, the only difference is you switch a plus to a minus. That's just math. And now we're ready, right? Now we're ready to go. So we have a simple mathematical question. Given that the evolution by Schrödinger's equation yields that starting with the device in its ready state and feeding in Z up, you end up with a state with an alive cat, and starting with the device in its ready state and feeding in Z down, you end up with a dead cat. What will happen if I feed in an X up electron? Okay. And we're forced to an answer here. We've already answered that question because it follows by linearity. Because X up is a linear sum of Z up and Z down as written there, then I can just write the initial state as a linear sum of Z up device ready plus Z down device ready. But I know how each of those pieces has to evolve. And so by linearity, it means that has to evolve in time to a state which is a linear superposition, 1 over root 2 cat alive state plus 1 over root 2 cat dead. And you just can't get out of that, right? There's granting linearity and granting completeness That's where you end up. And the problem is, suppose the wave function is complete and the final wave function that describes the cat system is 1 over root 2 cat alive plus 1 over root 2 cat dead. Then there's just no way to look at that and say that represents the cat being alive and not dead, or dead and not alive. I mean, the alive part and the dead part enter into that completely symmetrically. There's no sense in which that state is even more alive than dead. And therefore, you would reach the conclusion, if the wave function were complete, that the cat itself, at the end of the day, is no more alive than dead. And Schrödinger just said that was absurd, right? And this is a point where historically, in one of the great ironies of history, it's become fairly common for people to present this problem as if Schrödinger were trying to convince you that there are cats that are neither alive nor dead, which is exactly the opposite of what he was doing, right? Schrödinger didn't believe there could be a cat that was neither alive or dead. For Schrödinger, it was absurd to say that there could be a cat that was neither alive nor dead. What Schrödinger was doing was arguing that you can't both accept that the wave function is complete and accept that it always evolves linearly, because it leads to this absurd conclusion that the cat will not end up either alive or dead. John Bell, in a later paper, again, put it in a very nice way. The conclusion, as Schrödinger would understand it, is that either the wave function as given by the Schrödinger equation is not everything, that is, it's not complete, or it's not right, that is, the actual evolution wasn't linear after all. So this is now just to remind you what the problem of outcomes was as I originally gave it to you. Postulate, the wave function is complete. Postulate, the wave function always evolves in accord with a linear dynamical equation. Postulate that, if you will, experiments of this sort end up either with the cat being alive or the cat being dead. Okay, period, end of story. And you just can't hold all three. Not possible. So you got to give one up. At least one. You could give more than one up, but just logic is going to force you to give one of these up. And the nice thing about setting it up this way is it gives you immediately a taxonomy of ways to try to solve this problem by asking which of these is abandoned in this approach. If the answer is none of them, then you immediately know someone's made a mistake somewhere, because you can't keep all three. So let's look at the kind of general structure of solutions. You can deny completeness. This is what the Einstein-Podolsky-Rosen argument, in a very different way that had to do with locality, was trying to argue, is that the wave function does not provide a complete description of a system. If that's true, then even if the final wave function is 1 over root 2 cat alive plus 1 over root 2 cat dead, that doesn't mean the cat's not alive or not definitely alive or dead. It just means that that particular fact about the cat is not represented by the wave function. But the cat itself is in fact alive or dead. That means there must be something more, right? It just means that the health of the cat is determined by some additional physical facts that are not represented in the wave function. And that, if you assert that, if you deny the completeness, then you don't have a logical problem anymore. You have a physical problem, because you have to explain what more there is. Now, terminologically, again, historically, this whole thing is a mess. If you say the wave function is not complete, then of course you think there's more to the system than is represented by the wave function. Whatever represents that more, you can properly call additional variables, additional to the wave function. those additional variables traditionally were called hidden variables. And again, Bell remarks that that particular thing to call them is a piece of historical silliness, which is absolutely right. Why? Because they better not be hidden, whatever they are. Because one thing that sure isn't hidden is whether the cat's alive or dead. Right? At the end of that experiment, you know whether the cat is alive or dead. And if the physical facts that determine that are represented in these additional variables, then it's the additional variables that are manifest and obvious and easy to see, not hidden, the opposite of hidden. Okay? Because the cat's state of health is not hidden. Well, suppose I want to add these additional variables. Suppose I want to maintain the linearity of the Schrödinger equation, but I want to add these variables. What can I do? Well, various things have been tried and are tried, and you can, if you're laying awake at night thinking about what to do, you say, okay, I need to add something beyond the wave function to represent some physical features of the system. What are those features going to be? One obvious one is particles. You say, well, the cat is actually made of particles, electrons and quarks and so on. And these particles always have definite positions and follow definite trajectories, which is what classical particles do. And what those positions and trajectories are is not, certainly cannot be read off the wave function, so I'm going to use those as my additional variables. You don't have to do that. You could say, no, I don't like particles. They don't feel right to me. I think somehow ultimately physical reality is probably more field-like than particle-like. So maybe the cat is in some sense made of some kinds of, I don't know, electromagnetic fields that are not described by positions and trajectories, but are described by densities. And so people have used, in some cases, what are called matter density fields, where the matter density field of a live cat will just be distributed quite differently than the matter density field of a dead cat. And it'll behave quite differently through time. That's another thing you could do. There's a third possibility. Why this was come up with is something that would require another talk, but it was one that was suggested by John Bell again, of these things that are called flashes, which are just point events. So those are not particles and they're not fields. If you want to picture flashes in space-time, they're just dots. They don't form nice continuous trajectories and they don't fill all of space-time. They're just discrete point events. And you can fill space-time with these point events and then get something that looks like a cat that's either alive or dead without too much trouble. So these are all, and there are other possibilities. I mean, strings, fine. All kinds of things you might think that are in addition to the wave function. In order to play the methodological role you want them to play, you better be able to make, as it were, manifest cat-looking objects out of them. Because if you can't make things that look like cats out of them, then it's not clear how postulating them is going to help you get the result you want in the cat experiment.
Tim, is that the reason you put the dot after and?
No, that's just a typo. I told you there were typos.
No, but it was a well-placed typo, Tim.
Yeah. Yes, if you want to picture, yes, if you want to picture a flash, it's like a period. And so you know there's going to be a sense, if you go this way, there's kind of an obvious sense in which you'd say cats and boxes and vials and so on, and all these things are made out of the additional variables. Why am I postulating the wave function at all then? And the answer is, well, because the wave function is playing some role, some dynamical role, guiding these or determining their dynamics, which leads to words like the pilot wave theory, right? What is the physical point of having the wave function at all if it's not everything? And the answer is because it's playing an important role in determining what the other stuff does, and the other stuff is itself playing a more immediate role in making up cats and things like that. Okay. So that's one solution, and that if you do that, then you can stick with the Schrödinger equation or some other linear equation of motion for the wave function, which is very convenient because that's particularly simple and nice. A second solution is, so that's the solution that says the wave function is not everything. Another solution is to say the wave function is not right, and to deny the linearity, right? To say, well, what this shows us is, in fact, if you want to maintain that the wave function is complete, it can't always evolve linearly. It must do something else, either always or at least sometimes. And that kind of solution, which is a different kind of solution, are called objective collapse or objective reduction theories. And you're going to be hearing from Angelo Bassi very soon about experimental tests of objective collapse or objective reduction theories. Officially, I would say the Copenhagen interpretation is an objective collapse theory if you at least go and read von Neumann's classic Mathematical Foundations of Quantum Theory. It clearly presents a theory in which there is both sometimes linear Schrödinger evolution and sometimes nonlinear collapse evolution. That's just what's written down in the book. And von Neumann was clearly arguing, and in fact produced what he claimed were proofs, which aren't, that the wave function must be complete, that you can't add additional variables. Those proofs turned out to be wrong. So he certainly thought the wave function was complete, and he just straightforwardly denied that it always evolves linearly. Now, suppose you do that, okay, now that leads, just as adding additional variables leads immediately to physical questions like, okay, what are these additional variables? What do they look like? What's the equations govern them? If you say the wave function does not always evolve linearly, then you're going to say, okay, well, what does it do, right? And in particular, the way this historically played out was to think that there was a kind of alternation, that the wave function evolves linearly for a while and then suddenly does something else, and then linearly, and then something else in this kind of jumpy fashion. And then the question was, well, what triggers these collapses? Why does it go from a linear evolution to a nonlinear evolution? And this is a natural thought that occurs to you if you go down this road and you're going to change the dynamics. And the Copenhagen line, and this is where the word measurement comes in, is to say, well, it's upon measurement that these collapses occur. And that, of course, okay, that's a word, but that just poses the immediate question, what does that mean? When do measurements occur? What kind of physical situations, what kind of laboratory situations, what kind of non-laboratory situations constitute measurements? If you don't tell me that, and if you don't tell me that in very clear terms, then you don't have a clear physical theory at all. And that led, as I say, to a complete mess. One thing you can say is, oh, the wave function only collapses when a measurement occurs, and a measurement only occurs when a conscious mind becomes aware of an outcome. And then you've got consciousness thrown into this mess. And this was something that Wigner sort of played around with. And, Einstein would later laugh at this, and Bell does, and ask questions like, well, what about a mouse, right? Is a mouse conscious enough to measure something and collapse the wave function? Is a single-celled organism conscious enough? And these are questions you would have to answer if you go down that route. It just, I would not recommend it. I really think you're in enough trouble already without bringing consciousness into it. And this is the basis, if you want to go read John Bell's paper against measurement, Bell very forcefully argues that merely the word measurement showing up in a theory that's supposed to be a fundamental theory indicates you've made a mistake, because measurement isn't the kind of thing that's a fundamental thing. there are all kinds of physical interactions between systems, but there is no clean way to distinguish measurement interactions from other interactions. So does that mean we need to give up on this particular route? No. So we have this theory, the GRW theory, that was invented by Giancarlo Girardi, Alberto Rimini, and Tullio Weber. And this theory was first published in 1986, to give you an idea, and this is a long time after 1925 or 1935. But it very much impressed Bell. And the reason it impressed him was that they got out of this problem of measurement, of mentioning measurement, by getting out of saying there's any kind of trigger. That is, that there's any kind of environmental condition that produces collapses. That doesn't mean there aren't collapses. They just happen at random. They happen with fixed probability per unit time per particle, no matter what's going on. So a single particle in the middle of a vacuum doing nothing and interacting with nothing will occasionally suffer a GRW collapse. So that obviously takes any talk of measurement off the table. The main thing is to have these collapses occur at the right rates and in the right way to give you the results you want. And that's what Angelo is going to be talking about. It turns out that if you put these collapses in, that always means some predictions of the theory will be slightly different than predictions of a theory with no collapses. And so it means, in principle, a collapse theory always ought to be able to be put to experimental test against a non-collapse theory. But those tests turn out to be very difficult to do. You have to think up circumstances that you can actually access in the lab where these predictions will be distinguishable. And that's what work that's going on now. You may be familiar that Roger Penrose has been playing around for a long time with an objective reduction theory where the reductions are actually tied to something. They're tied to gravity. He never really came up with a cleanly articulated theory the way GRW did. But again, he got far enough along to start asking, okay, what kind of experimental situations might there be where you'd be able to notice that these collapses are occurring? Okay, so solutions 1 and solutions 2, right? So you have the additional variables solution and the collapse solution. And we have examples of those. You can read about them. People are developing them. You have non-relativistic versions that need to be put into relativistic versions. There's all kinds of work to be done. It's very clear when you work with these theories what they're claiming, how they work, what predictions they make. There's the third possibility, which is the last one, logically, and I don't have much to say about it, and I've put a question mark as to whether it's a solution at all. And that's to deny our last principle, right? Our last principle was that at the end of the day, the cat ends up either alive or dead. And it's not correct to say it's neither alive nor dead, and it's not correct to say it's both alive and dead. From a point of view of logic, it obviously resolves the logical problem to deny 1.3. The question is, what in the world are you now talking about, and how do you make physics out of it? If I can't look at a cat, right, put a cat in a box and do something and then check a little later to see whether it survived and say, oh, I just found out something physical about the world, the cat died or the cat's alive. If I can't do that because somehow it's not correct at the end of the day to say the cat just died or the cat just lived, then not surprisingly, the entire structure of physics is going to come under pretty heavy pressure. I mean, this is getting, from the get-go, you're suggesting that the physical world is very different from the way it presents itself to us in everyday life. And you better figure out how to get back something like everyday life out of this picture, or you just don't know how this theory is even going to connect to experience. Where this leads, obviously, people know, is this thing called the many worlds theory, where in some sense you say, you start out with one cat and you end up with at least two, if not an infinite number of cats, some of which are alive and some of which are dead. And the reason you never notice that is that you start out with one of you and you end up with at least two, if not an infinite number of yous, some of whom appear to see a live cat and some of whom appear to see a dead cat. That, in a kind of science fiction-y way, people feel like they have a grasp on. I don't really think it's very easy to make sense of that, even from the beginning. It becomes even harder when you get to the additional problems, which I don't have time for today, but I'll just mention this one, right? There's the quantum theory standardly makes statistical predictions. So it will say things like, if you put this kind of electron through a Stern-Gerlach apparatus, 25% of the time you'll get a flash up and 75% of the time you'll get a flash down. And that's the kind of thing you would normally go into a lab and check and count and say, oh yeah, that's correct, or no, that's incorrect. If every time you do the experiment, you both get an up and a down, as it were, there's an up result in one world and a down result in another world. And when you do a sequence of experiments, all the possible outcomes occur, all the possible sequences occur. It's not even clear what you mean to say that 25% of the time it was up and 75% of the time it was down. Not clear what the content of that is. So you clearly have very deep conceptual problems that have to be faced, which you do not have at all on either of the first two ways of getting out of this problem. Okay, so that was as much as I thought I could do carefully and slowly today, and I did it slowly enough. And it leaves us with, I guess, a little time to take questions. I could go on to some other topics in the area, but I really want to make sure everybody's on board with this, because if you're on board with this trichotomy, it really gives you a leg up in approaching any proposed solution, because the first question you ask is, okay, are you denying the wave function is complete? Are you denying the wave function evolves linearly? Are you denying that the cat ends up alive or dead, or the flipped coin ends up heads or tails? Right? And if your answer to all three of those is no, because you don't like saying yes to any of them, then you just haven't solved the problem.
Well, Tim, let's pause and let everyone unmute yourself, and let's thank Professor Maudlin for this presentation, and then we will